Thanks everybody for coming to the talk. Thank you for the introduction. So today I'll be talking about commuting local Hamiltonians beyond
Recording in
Bostanci.
progress.
Great. And this is joint work with John Bostanci at Columbia University. So let me just give a brief outline of the talk. I'll first try to motivate and introduce the commuting local Hamiltonian problem, which is a variant of the very well-studied local Hamiltonian problem in quantum complexity theory. I'll state our results and also try to give you an idea for the results and the proof idea behind it, which kind of goes back down to considering some lattice of a Hamiltonian and introducing holes by puncturing the Hamiltonian. And I'll describe this more in detail later. Finally, I'll conclude with some open questions as well as directions for next steps. So the commuting local Hamiltonian problem, like I said, is a variant of the local Hamiltonian problem. And there, the objective is to find some ground state for the Hamiltonian. A Hamiltonian is given by some term H, which is a sum of Hermitian matrices, Hi. And we inherit the same conditions from the local Hamiltonian problem. So each Hi should have bounded operator norm and act on some constant number of qubits. The difference here is that we require that these terms commute. So commute means that each of these, for every ij, we should have that the commutator, hi, hj, should be equal to 0. So their product commutes with each other. In a sense, this generalizes classical CSPs in the sense that if you have a classical like 3-sat instance, a constraint satisfaction problem, you could always imagine writing the constraints as some diagonal matrix. And these diagonal matrices commute because they are diagonal. So this is somehow a generalization of classical CSPs. The difference, of course, here is that there's not going to necessarily be a easy to find basis in which you can diagonalize the Hamiltonian. This is a kind of a strong restriction. Nonetheless, it's very well motivated, and it's a class of Hamiltonians that's been well studied in the past. For instance, the Hamiltonians for any quantum code is generally going to be commuting. An example of this is the Tor code. This is a particularly useful example because there, the ground state exhibits a lot of entanglement and is known to have topological order. So in some sense, even though commuting Hamiltonians generalize classical CSPs, they still retain a lot of the interesting artifacts of quantum computing and quantum information. Additionally, we've also often used commuting local Hamiltonians as a way to study very complicated questions in quantum theory. For instance, a lot of the progress in Gibbs sampling has been made by studying commuting Hamiltonians as an interesting test case. Finally, I want to note that a lot of progress in the quantum PCP conjecture, probably the most important question of our current time, came from studying commuting Hamiltonians, and the progress recently made in the NLTS conjecture also came from studying commuting Hamiltonians. So given all of this and the interest in this area, like what is the complexity, the inherent complexity behind the commuting local Hamiltonian problem? One thing you can say is that because the local Hamiltonian problem is QMA hard, it's at least that, or it's at most that hard. But there's reason to suspect that it might fall in a lower complexity class as well. For instance, like I said earlier, if you knew the basis in which the Hamiltonian was diagonal, then this kind of becomes a QCMA problem, right? Because the prover could just tell you the classical description of a basis state. It's simple because it's diagonal. And then you, the verifier, could verify that yourself. But it's not obvious here because, again, the basis that it's diagonal in might not be easy to find. So the one very interesting line of work has been in showing that more and more families of commuting local Hamiltonians are actually contained in MP. This is very interesting, and it shows that it really has a lot of characteristics of classical optimization problems with this commuting restriction. One of the first pieces of progress made in this area is in studying the very restrictive 2-local case. This is due to Bravi-Viali, and they showed that if you have a commuting local Hamiltonian where every term only acts on 2 qubits, then finding the ground state is a MP hard, and it's contained in MP as well. So this was a very important result, and it led to a lot of follow-up work where they showed that other families of Hamiltonians are also in MP. For instance, we know that the 3-local qubit case is also in MP. This is due to Elharanov and Eldar, as well as the 2D lattice Hamiltonian on qubits, as well as 2D Q-trits. One thing I want to point out is that aside from the first work, which worked for any qubit dimension as long as it was 2 local, these last 3 works, or the last 4 works, all work with a restriction on the dimension of the qubits. So here, the first two are with q bits, and the last one is with q trits. And we'll see later that, in a sense, this is not really an artifact. This is really an important part of their proof and how they analyze the structure of the Hamiltonian. So these results might lead you to believe that maybe the problem as a whole is contained in MP, but there are other cases where, beyond the local Hamiltonian problem, which is a ground state optimization problem, where we do know that commuting Hamiltonians do share the same complexity as the general class of local Hamiltonians. For instance, in the ground state connectivity problem, we know that both for CLH and for local Hamiltonians, these problems are both QCMA hard. So in this case, the complexities actually do coincide. I'll often abbreviate commuting local Hamiltonian as CLH, just so I don't have to keep saying that. So in our work, we make progress in this by showing that a slightly larger family of Hamiltonians is also contained in MP with the commuting restriction. First, we show that for 2D rank 1 CLH, this is an MP. I'll specify what the rank 1 constraint really means here, but I want to emphasize that these two results both do not rely on the dimension of the qubits. So we lifted that restriction from the prior works. Additionally, we show that we can extend this work to 3D, and we also get that 3D rank 1 CLH is an MP. And just very quickly, rank 1 here is referring to the matrix rank of the Hamiltonian terms. Let me describe these pictures. So the picture on the left is an example of a 2D lattice Hamiltonian. So you should imagine that the Hamiltonian terms are on the faces of the lattice, and the qubits are on, or qudits are on the corners of each face. This is an example of a 3D Hamiltonian, and here the volume is a single Hamiltonian term, and the qubits are now on the edges of the Hamiltonian. So what is our high-level objective, and what is like the overall proof idea in showing that these Hamiltonians are contained in MP? Well, we follow something similar from the work of Harnov, Kenneth, and Vidorovich. They were on a few slides back, and this was a paper which showed that 2D lattice Hamiltonians on qubits is an MP. And the overall idea there was to take the 2D lattice Hamiltonian and puncture holes in the Hamiltonian. Why do we puncture holes? Well, the idea is that somehow doing these puncturings might simplify the Hamiltonian and make it more amenable to analysis. Suppose you have a 2D lattice Hamiltonian. So this is, again, given by Hamiltonians on the faces and then qubits on the corners. Then I claim that if you are able to puncture enough holes in this lattice, you can actually generate a 2-local Hamiltonian from this. This is very useful because I stated earlier that we know that any 2-local Hamiltonian, two-local commuting Hamiltonian, is contained in MP. So this would automatically allow us to conclude that the resulting punctured Hamiltonian is also in MP. So I puncture a hole, and then what I do is I draw these lines going through the lattice, which subdivide the grid. And the important point here is I've color-coded these qubits. So these are all green, these are all red, and these are all orange. And the point here is that if I subdivide the grid in this way, and then group all the qubits of the same color into one larger qubit, then the resulting interactions are all at most 2-local. Because this interaction is all acting on qubits of the same color, so this corresponds to the same big qubit, and thus it's now 1 local under this grouping. Similarly, any term that crosses this boundary is only acting on 2 different colors. So after this grouping, those cross-boundary terms are now 2-local. So by puncturing and grouping appropriately, we've now generated a 2-local interaction on qubits of higher dimension. One thing I want to point out is that you might object to this by saying that, okay, if you have a larger and larger grid, then these groupings become very large. And now we have qubits that have dimensions scaling with n, which you might not want. The point is that if the grid is bigger, you just puncture more holes. As long as you puncture enough holes in the lattice, the groupings can be made to be constant size, and therefore it's a constant locality Hamiltonian. Now let me discuss the main technical tool behind this. And the structure lemma has really been fundamental in a lot of the analysis and all of these results in commuting Hamiltonians. Pretty much any paper that studies commuting local Hamiltonian, including ours, uses the structure lemma. I won't have time to give the full details of the structure lemma, but let me give you a high-level idea of what it really does. So let's suppose that we have these two operators. I call it PA and PB, and the subscripts represent the qubits on which these interactions act. So these are two local things. PA acts on qubit 1, 2, PB acts on 2, 3. Suppose it commutes, then this structure lemma tells us that they are block diagonal, at least when you look at the Hilbert space corresponding to the second qubit. In particular, they take a very nice form. So PA has this block diagonal form and PB also is block diagonal with like a consistent block diagonalization. And the important part here is that if you look at a single one of these blocks, PA and PB act as product operators. So here I've written that PA is like A2 tensor identity, PB is also identity tensor PB2, and you should notice that these two act on disjoint subsystems. So the structure lemma tells us whenever you have two commuting operators, there is some projector that you can apply, such that after applying the projector, you now have decoupled these interactions. This is a very powerful theorem, and it tells us that these commuting operators are very well structured. Okay, let me show an example of this, so maybe help understand. So let's look at this very simple case of 1D Hamiltonians. In the 1D case, you again have PA and PB. So PA acts on qubits 1, 2, PB acts on 2, 3. And suppose they commute, and therefore they intersect on Q2. We apply the structure lemma, and the structure lemma tells us that the interaction PA will decompose into blocks that are consistent with the decomposition for PB. And moreover, if we look at a single one of these blocks, so this is a Hilbert space corresponding to some direct sum index I, it tells us that if we look only at that subdivision, then the interaction PA and PB, they decouple. So this gives us kind of an idea how to tackle the local Hamiltonian problem. Because remember that in the local Hamiltonian problem, our goal is to find a global ground space. So what we want is that the proof should be an identifier for which of the direct sum subspaces the ground space intersects. If they tell us that, the verifier can project down their interaction only to this Hilbert space, and they've effectively decoupled the 1D Hamiltonian. I've only shown this like interaction with two Hamiltonian terms here, but you can easily imagine there being like a chain of operations, and the prover just goes down the line and tells you for each qubit which subspace to project down onto. And now you have a collection of decoupled Hamiltonian terms, and you can verify the ground state locally. Okay, so this kind of gives us a blueprint for what we might want to do when we extend to higher localities beyond 1D, because that's kind of a very trivial case. So now imagine you have this cluster of three terms, PA, PB, and PC. One thing you can try to do initially is do the same thing we did before. So we have PA and PB. They intersect on Q1 and Q2. So let's try applying the structure lemma to just this subspace. And this gives us a decomposition, and the prover can give us a projector, which allows us to decouple the PA-PC interaction. The problem with this is that PB also intersects on Q2, right? So whatever projector that the prover gave to us is going to somehow impact the PB projector as well. Somehow we can't like just ignore PB and only decouple PA and PC. This is an issue because it tells us that the structure lemma is giving us a projector which works for only this pair, but might not be consistent for the global Hamiltonian as a whole. You can try to extend this by saying, okay, what we'll do now is consider all three things, PA, PB, and PC. And it's easy to see that the structure lemma extends to three terms as well, and therefore you get some decomposition of the joint Hilbert space on Q1, Q2, and Q3. This is fine, but the issue is that the overall Hamiltonian is a lot bigger, so there could easily be a fourth gray term down here, and now you have to like extend this decomposition even further to Q4. And so you slowly have to like increase the size of the subspace that you're performing this decomposition on until you get some like decomposition of the full Hilbert space, and that's not something that the verifier can check themselves very efficiently. So this becomes an issue whenever you have these like overlapping terms that do not intersect consistently. It becomes very hard to apply the structure lemma very easily. However, there are some nice tools that previous works have used to study this interaction, and this is kind of where they use the restriction on the qubit dimension. If you restrict the qubit dimension, then the decompositions you get from the structure lemma become a lot easier to analyze and to argue about what kind of inconsistencies you might get when you look at other terms. So let's try this out. So now we have this like four-wise interaction where they all intersect on Q2. What we'll do is, because the p-type terms only intersect on Q2, right? Like there's no, okay, you can imagine there's qubits here as here and here, but PA and PB are diagonal from each other, so they only intersect on this qubit. And so we can, oh, okay, well, something weird happened with the font, but what you can imagine is that the structure lemma gives you some decomposition of the Hilbert space on Q2, and therefore the prover can tell you how to decompose at least Q2 if you only cared about PA and PB. The nice thing is if Q2 is a qubit, then the structure lemma doesn't have a lot of flexibility. Remember that the structure lemma gives you a block diagonal decomposition, which means that the overall dimensions on that qubit need to sum up to 2, right? So in particular, if this is a qubit, then the structure lemma can only give you a like 2-dimensional and 0-dimensional, or 1-dimensional and 1-dimensional decomposition, just because it needs to add 2. This means that the decompositions that the structure lemma induces on Q2 are quite simple, and is something that you can kind of work out through cases. The very nice thing is that in the 2-0 case, one of these terms kind of cancels. And in the 1-1 case, these prior works, particularly Aharonov, Kenneth, and Vigdorovich, they notice that if the decomposition on Q2 is like this 1-1 decomposition, then these interactions actually kind of behave like the toric code. So they notice that by studying the local decompositions you get from the structure lemma, you can argue that the overall Hamiltonian up to local unitaries is equivalent to a toric code. This is very nice because earlier we pointed out that if you could do this puncturing, then you get a Hamiltonian that's in MP. The issue was that it's not clear how to repair these holes, right? Because overall, our goal is to prove that the original Hamiltonian was in MP, not this like weird punctured version. So the goal would be for you to puncture the holes, prove that this thing is in MP, and then like show how to repair the holes at the very end. But in this particular case, when you have this restriction on the lattice as well as the qubit dimension restriction, then AKV argue that this overall Hamiltonian is similar to the toric code, and therefore to repair these holes, you can apply the toric code corrections. So here in this very special case, they argue how to repair the holes at the very end of their process by these like string of poly operators like you do in the toric code. Okay, so in our work, we do something somewhat similar, but we notice something, which is that you never have to fully remove terms, actually. Like, instead of fully removing the term, all you have to do is create enough wiggle room such that you can put the corner of the boundary within that hole. I guess I didn't mention this explicitly earlier, but I want to point out the reason why we do this puncturing at all is that if we didn't puncture this at all, then this term that's on the boundary of these 3 lines would act on 3 different colors, right? So we always need to, the boundary needs to be placed in a way such that it goes into a hole. Therefore, every remaining term that the hole is not involved in is actually true local. Okay, so then this motivates our overall objective, which is to show that given a qubit Q, so you can just imagine the qubit Q being some qubit intersecting this hole or this boundary, we want to show that we can puncture a hole in all of its neighbors. I guess the math is not showing up correctly. That's what's going on. Okay, so let's see how to do this, at least for this particular case. So the idea here is to apply some projector pi q to just this qubit, and we'll choose pi q based off the structure lemma decomposition from just PA and PB. So we're ignoring QA and QB for now, but let's just pick pi q to be one of these, the projector onto one of these direct sum subspaces that came from the structure lemma. The trick here is that after applying pi q, the remaining terms, QA and QB, are not consistent with it, right? Like pi q came from applying the structure lemma to these 2 terms, so there's no a priori reason why QA and QB should be consistent with this projector. The thing that we use, and the new technical tool that's different than the prior works, is that we analyze how to round the remaining terms via an applications of Jordan's lemma. And we'll see how this works later. Okay, so this idea has some technical complications that we need to iron out. First, how do we ensure that this transformation is sound and complete? if the original Hamiltonian had a 0 ground state, how do we ensure that the resulting Hamiltonian also does? And if it didn't have a 0 energy ground state, how do we ensure that the new Hamiltonian also does not? Additionally, a recurring theme in our work is going to be this idea that we want to always retain commutivity when we're doing these transformations. So we also need to argue that when we apply this projector pi q to qa and qb, the resulting Hamiltonian still retains commutivity. Okay, at this point, I'm going to introduce the main assumption that we use in our work, which is this idea that all terms are rank 1. To reiterate, when I say rank 1, what I mean is that the Hamiltonian terms themselves have bounded rank. In particular, they're just like a projector onto a single state. Why do we do this? Well, first, it simplifies the analysis of the algebra. So in a sense, this is kind of like a orthogonal assumption to this assumption that we have bounded q-dit dimension. Instead of having a q-dit dimension bound, we instead bound the rank of each term. There's some motivation for this, one being that for both MP and QMA, we know that there are families of complete problems which are rank 1. So in a sense, we don't lose any complexity, at least for MP and QMA. One downside is that we've done a little bit of digging, and it's not clear that there are like nice physically motivated Hamiltonians, which are commuting in rank 1. We're always open to hear people's ideas if there are any interesting physically motivated examples, but we couldn't find any. And then lastly, the big question with this is whether this assumption is without loss of generality. Like a dream would be showing that actually the rank 1 terms, the rank 1 commuting Hamiltonians are actually complete for CLH, which would show that all of CLH is in MP. Okay, so what do we do with this assumption? Well, recall that by rank 1, PA is like a projector onto some Kepra psi, and PB is also a projector onto some Kepra phi. And again here, this is some state psi that's acting on qubits 1, 2. This is some state acting on qubits 2, 3. And what this assumption buys us is that it tells us we fall into one of two cases. The first case is that PA and PB are both tensor operators. So PA is exactly some psi tilde tensor U, and PB is some U tensor phi tilde. Or the other possible case is that they're actually orthogonal to each other. So PA and PB are just entirely orthogonal operators. And you can imagine this as thinking about the block diagonal decomposition, where one of them is non-trivial only in the first block, and the other one is non-trivial only in the second block. This allows us to classify the interactions as being either, we call it singular or reducing. Singular being the first case where this middle interaction area is rank 1, and reducing being the orthogonal case. Intuitively, when we say reducing, we call it this because this means that the prover can give us a projector under which one of PA or PB is completely eliminated. Okay, so let's consider these two diagonal terms, PA again and PB. Here I called it psi and psi prime. Since they commute on Q2, we can apply our key property on Q2. And this tells us that the decomposition goes in one of two ways. The first is singular, which means that psi acts as psi tilde tensor U, and PB acts as U tensor phi tilde, but they're both living in the same. Is it working again? Okay, cool. Okay, so right, the prover gives us projectors, pi p and pi q. And because this is a reducing version, we're allowed to completely cancel out like one of these pairs of terms each. So without loss of generality, let's say that we only are left with PA and QA. Okay, so you might say that we're done now. We've like canceled out PB and QB, so we've punctured a hole in the Hamiltonian. The issue and the technical subtlety here is that we've done this in a way which is inconsistent, right? Because this projector, pi p, it's the projector we got from the p-type decomposition, and pq is a projector we got from the q-type decomposition, but they're both projectors onto the same qubit. They're both projecting q2. But they're not necessarily consistent with each other. There's no reason why they should like play nicely with each other, and therefore we need to somehow argue that there's like a single reduction we can do, which simultaneously cancels out QB and PB. Okay, and this is where Jordan's lemma comes in to save us. Remember that the goal of the local Hamiltonian problem is again to find a global ground state. We call it, or like a consistent ground space. And so what you can do is instead of looking at the Hamiltonian terms themselves, you can look at what the good subspace looks like. So this is essentially the local subspace that corresponds to the ground space. Normally, it's like identity minus the Hamiltonian term, but because we've done this restriction, the good subspace now looks like pi p minus PA and pi q minus QA. So this just, you can imagine there being like a unwritten tensor identity there. But essentially what we've done is reduce the local Hilbert space to only include PB or pi p or pi q. And the goal here is to argue there's a global, consistent, good subspace for both pi tilde and q tilde. We do this by applying Jordan's lemma to find a consistent ground space. And more specifically, Jordan's lemma, when we look at the product of these two good subspace projectors, it gives us some like block diagonal decomposition where some of the blocks have 0 eigenvalue and some have non-zero eigenvalue. And we use Jordan's lemma to look at the non-zero Jordan blocks and take the merged projector, which is at the union of all of those good subspaces. There's some technical details to wring out. Like again, we need to make sure that the resulting operator commutes, soundness and completeness, but we're going to ignore that for now. And now we've done kind of what we wanted, which is we've punctured a hole, and we've also merged PA and QA in a way such that the Hamiltonian is commuting. Okay, and finally, my last point is that we can do a similar process in 3D, which is instead of puncturing holes in just grids, what we're going to do instead is take slices of some like larger array of cubes and puncture a hole all the way through those. We still run into an issue because there might be obstructions. Like now when I do this merging, you can imagine this green thing is H merged from a previous step, and this blue one is H merged from a different step. But now there's like no consistent hole we can weave. The point is that, and I emphasized this earlier, the point is that we've always retained commutivity when we're doing this reduction. So we can now look at this local picture right here with the green and blue term and do the same puncturing argument on these two pairs, which will allow us to puncture a hole. So I think this really emphasizes a key point, which is that rounding schemes should take commuting Hamiltonian and produce another commuting Hamiltonian at the end. I think high-level message, which is that we have a very robust theory of NP reductions, right? We know how to take NP problems that are complete and reduce them to other NP complete problems, but we don't have a similar technique for either local Hamiltonians nor for commuting local Hamiltonians. And we believe that this work is like a first step in like developing a more robust theory of maybe something similar to gadget reductions for Hamiltonians. Okay, next steps. I mentioned the first thing. The second is that every work has primarily just used a structure lemma. In ours, we introduce other quantum information theoretic tools like the Jordan's lemma. I think there's a very wide range of techniques that could be applied to understand commuting local Hamiltonians better. What other tools are there? And that's about it. Thank you very much.
Okay, any questions?
Hi, sorry. So maybe I missed it, but how do you like? I think you mentioned that by puncturing your hole and you could partition your interactions into qubits with multiple colors, and you were grouping those based on those colors. Now I missed it. Why does it not explode to qubits of very, very high dimension?
So the idea was that for that simple example, I only punctured one hole, so this required 3 partitions. But in general, and if you look at the paper of Aharonov, Kenneth, and Vigdorovich in particular, they have a very nice picture. But the point is that if you have a bigger lattice, you just puncture even more holes, and then you like imagine connecting all the holes with lines. And as long as there are enough holes in the lattice, then each grouping is like constant size. So for this particular picture, there was only 3, but like if you have a much larger grid, then you like puncture on the order of like n squared holes, and therefore each individual subsection is constant size.
Yeah.